before is called the mean value theorem. But wait, didn't we talk about mean value theorem already? Did you have a question in your last exam about mean value theorem?
Yes.
But that was the mean value theorem for derivatives.
Yep.
Find a C that between A and B makes the derivative the average rate of change, right? Fine. So now we got a mean value theorem for integrals. So the main thing to keep in mind is that when it comes to derivatives, you're finding the mean value of the rate of change. You're finding the mean value of the rate of change of the function. Here you're finding the mean value of the function itself. Okay? So the mean value theorem for integrals is the mean value theorem, mean value of the function itself. That's the main difference. Question will be like this. Number 19. Find the mean value of the function is 1 on x. Over the given interval. One to e. Interval from 1 to e. We graphed 1 on x a minute ago. We graphed 1 on x cubed. They're basically the same thing. The function looks like this. Here's 1 on x. So we're going to go to 1 here, and then 2, 3. So I guess e is in here somewhere. Here's e. Okay. So what are the mean value the function takes on? What's the mean value of the function? Not its slopes, not the mean value of the rate of change, right? The mean value of the function itself over this particular interval. Okay, so the formula is mean value of f of x on AB is the integral from a to b of that function. So we're going to find the area between the curve and the x-axis. Okay? That is part of the formula, standard integral. And then we're going to divide that result by the length of the interval, 1 over b minus a. Right? Net area on AB divided by length of interval. Okay? That's what it means to be the average value of the function. So first let's find the integral. So we need to find integral from 1 to e of 1 on x dx. That will be the right-hand portion of the mean value. Then we'll just divide by the length. So e minus 1. Right, what is the antiderivative of 1 on x?
X.
Isn't it? Wait,
Oh,
no.
I mean,
Isn't it ln?
Yeah, ln.
ln x?
What?
Close.
Or actually,
Super
1
duper-
over x squared.
No, you were closer.
I thought it was ln x.
It is, but there's a little twist on it.
Let's see.
No, not for what we have for these guys here. Remember absolute value.
Why? Oh.
We don't know if x is
So in this problem it doesn't matter because all the x's are positive. So this problem doesn't matter. But in general, you probably weren't thinking about it in the first place. So in general, you should be careful.
The absolute value.
What's it? Why?
Yeah, why is it the absolute value again? I forgot.
Oh dear. Why is it the absolute value? So the reason is,
Or is it just because?
no, it's not just because. I mean, there is a reason. So, if we ask, what is the antiderivative of 1 on x? Forget the limits of integration. We're claiming it's ln of absolute value of x. So, what we're trying to find here, I'm going to draw this up on the side. What we're trying to find here is a function. I need to find a function that when I differentiate, when I take its derivative, gives me this function, right? With me on that? You will be in a second if you pay half attention. Let's look at ln absolute value. What does ln absolute value of x look like? Well, it looks like it's 1. Over here at negative 1, so now absolute value looks like this. Okay? There's ln absolute value of x. Still got its asymptote there, right? So let me ask you a question. If I took regular ln x, right, this, right, just the right-hand portion, that's the regular ln x, right? And I differentiate it. I take its derivative. What do I get?
1 over x.
Right. Right. 1 over x. What does 1 over x look like? It looks like this. Hey, it's got 2 sides. Look at that. How can I possibly take the derivative of a one-sided thing, that's only got the right-hand side, and I get a function that has both sides? Not possible. There can't be values for slopes where there were no slopes in the first place. Okay? So every time you took the derivative of regular ln, I meant, before we got to this section, every time you took the derivative of regular ln, it yielded 1 on x, but it only meant the right-hand side, and you just didn't say it. Because these are the values of the slopes for these slopes here, right? These slopes along this curve have these function values, 1x function values. But now if you start with 1 on x in the first place, right? You're starting with 1 on x. You're starting with this entire picture. And you want to know, what is the function that you differentiate to get 1 on x? And I want the whole picture. I don't just want half of it. What must it be? I got to fill in the other side of the picture. So that's what absolute value does. Absolute value inside this function gives you both parts here, so when you were to differentiate it, you would get to both of these pieces. Right? That's why.
You didn't let go.
Now, 0 is still a problem. There's still no such thing as ln of 0, and that's because of the asymptote here. So even though it has the absolute value, it does not clear up the 0 case. It clears up all the negative cases. Now all the negatives are just fine. Right? Put a negative in here, no big deal. The 0 is still a problem. And that's why you need the absolute value, because you're taking a function whose domain is everything except 0, and you want to get out an antiderivative whose domain is everything except 0, not just all reals, not just the right-hand side. Okay, enough of the whys. Let's just do this problem. So, forget understanding. Let's just put these numbers in. 1 to e, right? So I need ln of absolute